parallel, because if one goes out, you still want the other one to be on, right? So one of the things about series circuits, right, if you have a series circuit, if one of the bulbs burns out, that literally means that it melts and leaves a gap in the circuit. We call this an open circuit. So make sure you understand that terminology. It's not like open for business. This is not open for business. It's like an opening or a gap. And the moment there's an opening or a gap, then the charges immediately sense that there is no viable path, and so the current goes to 0. So something like Christmas lights, they certainly look like they're in series. And then, by the way, the reason they look like that is because they used to be in series. Okay? You used to have the charges flowing through one light after another. The problem, of course, is if one thing goes out, then they all go out. So the old school Christmas light sets, this is like 100 years ago, you used to take out your replacement bulb, carefully unscrew every one, and then screw in the replacement. And if the whole thing turned on, that was the one. And if not, keep going. God forbid 2 lights burn out at the same time. Okay? So, in fact, Christmas lights, even though they look like they're in series, every single bulb has a viable path across the entire battery source. They actually wire them in this weird way, where here's one bulb, here's another bulb, right? They all are a viable path. They're all in parallel. They just are made to look like they're in series. If you actually unwound that thread that connects them, you'd find a whole bunch of more smaller ones in the middle. You can make something look like it's in parallel, in series, even though it's actually in parallel. All right? Now, you might think of that and say, okay, it seems like parallel is the way to go, right? Everything is independent. If one thing breaks, then it doesn't break the whole thing. But sometimes that's a feature and not a flaw. Let me show you. So let's say we have 2 things in series. And those 2 things in series are some very expensive thing you bought, and this thing you buy from the hardware store, which is called a fuse. Usually costs like a couple cents. A fuse is something that is designed to accommodate only a certain amount of current. So that current, of course, is going to be set by whatever it is that you're planning to connect it in series with. And that fuse is going to dissipate P equals I squared R. It's going to dissipate a certain amount of power. So the fuse can take a certain amount of current because there's a certain amount of power that it can dissipate safely to the environment. So it gets hot, but not too hot, and the heat can be dissipated out into a normal room environment. But the whole point of this is it's rated to, say, a 5 amp fuse. So if you have a 5 amp fuse, if there's something that goes beyond 5 amps, the power dissipated is designed to melt the fuse and cause an open circuit. That's the whole point of it. Why is that a good thing? Because if you have an unexpected surge in current, you want this to burn out and shut off the current, because you'd rather that power be dissipated in a 5-cent fuse than your entire expensive device. Okay? So there, it's a feature that when one thing in a series goes away, it knocks out the whole thing. It knocks out the whole chain. Okay? The circuit breaker in your house is basically the same idea. A fuse is something that you buy. You want to make sure to always match the right fuse, right? Because the fuse has to be matched to the right device. If the device will be damaged by a current in excess of 5 amps, don't put in a 10 amp fuse, because the 10 amp fuse will let in 10 amps to go through that thing and it'll fry it. So you always want to match the fuse with what the device recommends. You can also, by the way, if you're buying fuses at the hardware store, first of all, you got to get the right amperage. So does the device require what kind of fuse? The second is there's a fast blow and a slow blow fuse. So you got to find that too. For instance, a 5 amp slow blow fuse, it will allow 5 amps for a relatively short period of time before, and then it'll go out. Whereas a fast blow will immediately cut out. So the idea is if it's okay for the current to fluctuate for a little bit but not too long, then you want to put a slow blow. Fast blow is going to be too aggressive. It's going to blow out too unnecessarily, right? That's just annoying because you have to keep going and buying new fuses. But the last thing you want to do is put a slow blow fuse in where you need a fast one, because that could allow damage. So some devices are just more sensitive than others in terms of how long they can tolerate a current surge. Okay? So these are all things you're considering. Now the circuit breaker in your house is not a piece of metal that literally melts. That's what, if you've ever seen a fuse, it's literally just a little glass thing with it has a little metal filament in there, and the reason it's glass is you can see in there to see if it's melted and know whether to replace it. A circuit breaker is a mechanical thing, okay? When the current exceeds too much, so it's usually written on the circuit breaker box, it's like 25 amps or 50 amps or something like that. If it exceeds that, there's something mechanical that swings open and causes an open circuit. Then you can go down to the basement or wherever and put it back. You don't have to go to the hardware store. It's a mechanical release that you can reinstate. So I'll give you an example. So here is, let's say you plug in a power strip. Oh, I guess let me ask you this. When you plug in stuff in a power strip, is that in series or in parallel? Parallel, right? You plug in your toaster and your TV into your power strip. When the toaster pops, it doesn't turn off the TV, right? They're independent things. So you plug in your toaster, and you plug in your TV, and you plug in your hair dryer, and you plug in another hair dryer, and another hair dryer. Okay, so that's not good. The total resistance is going way down, and the total current is going way up. Now you might say, what's the big deal? Because that current is, of course, also being split across all these branches, but it also is flowing all through your household wiring, right? So having a huge amount of current flowing through your household wiring, which, yes, it does have resistance, is going to cause an issue. So this, again, is exactly what we were talking about before. We have a series circuit. We have your household wiring, and we have all the stuff that's going into your power strip. And as we decrease this resistance of this section, we're going to decrease the voltage drop across here, which means we're going to increase it over here. Okay? If you want to look at V equals IR for the wiring, you can think of it as that it's not that the resistance is changing, but the total current we already said had to be increased, and of course the voltage drop is going to increase, and the power is going to increase. And at some point, you risk literally starting a fire behind the walls because the wiring is getting so hot and it's in an enclosed space. So at some point, whatever licensed contractor has built your home, hopefully, has appropriately matched up what current the circuit breaker will trip at to prevent the wire from getting too hot. Okay? Does that make sense? Okay, so this is really a parallel section, but this parallel section is in series with this. And if you're lowering the resistance of this section, that takes less voltage drop, this takes more. Okay? Okay, so those are some practical everyday implications. Let's do another conceptual example, and this one I'm going to hook up so you can see it in action. This is my second conceptual example, I suppose. I'm going to have this. And again, when I close the switch, I'm going to ask what happens with I1, I2, let's list them in a row here, I1, I2, V1, V2, P1, P2. I'm going to close this up. Well, let's get a flavor first of what was going on before we close the switch. We're going to have our classic series circuit. We have three distinct equipotential regions, A, B, and C. We have a high, middle, and a low. Looks something like this. I guess let me draw it over here. High, middle, and low. A, B, C. So we will, of course, establish a certain amount of total current and a total amount of resistance. I guess, why don't we even add to the list? I total and R equivalent. So the equivalent resistance at first will, of course, just be the sum of R1 plus R2, and the total current will just be determined by that. Okay? So, when we connect the switch, we essentially are merging equipotential regions B and C into a single one. So basically there is no B anymore. So when we close this, like so, C will extend its reach all the way over here. This is still C. So what I've essentially done is we've given a free shortcut around resistor 2. There is no reason anymore for anyone to go through resistor 2 when they have a free ride going around the path of no resistance. So the voltage drop across 2 will actually decrease to 0. The same equipotential region can be found on both sides. There is no longer any motivation to go through that one. So what happens to the current through resistor 2? If you take away the motivation, nothing's going to go through there, right? Remember, V equals IR. If V is 0, so is I. That's going to shut off. And, of course, the power is also going to decrease to 0. In fact, it's not at all going to be in the circuit electrically anymore. Nothing passes through there. The total current, nothing will, whatever it is, will all go through here, and none goes through here. Now, if you want to think of this in terms of parallel, if you want to think of it as R2 is in parallel with that straight piece of wire, you can do that too. That's one interpretation. We said that more current goes through the easy way. We made the point that some still goes through the hard way. This is the exception because one way is completely free. So not only does more current go through the straight wire, all of it does. Okay? The more sophisticated way to think of it is that these two equipotential regions have merged, and so therefore there's no motivation to go through R2 anymore at all. So that's one thing we're expecting. This construct, by the way, is called a short circuit. You may have heard that term. Short circuit, it's like, think shortcut. The charges have a shortcut around R2, and so nobody goes through R2 anymore. Now, short circuit has the connotation in our everyday language as being a bad thing. I would say it's neither a good nor a bad thing, it's just whether or not it's something that you want, okay? So I'll talk about that in just a second when I hook it up, but let's make sure we understand what happens to the rest of it. Well, if we've essentially merged B down here, this has decreased and this has increased. In fact, now the entire voltage drop will be across R1. There's no voltage left to drop after you've gone through that one. So V1 is actually going to increase all the way up to the entire battery voltage. And if you look at any of the formulas with V squared over R, you can see that the power is going to increase as well. Power is going to increase all the way up to this. Okay? As far as the total current is also going to increase, and that's because there's one less resistance in the way. Our equivalent resistance is now just R1. R2 might as well not even be there, because nothing actually flows electrically through it. The only resistance in the way of the flow now is R1. The total current is going to increase up to that dictated by R1, and the current, of course, here is going to increase as well. I guess I should clarify that I1 and I total are the same thing anyways, because there are no forks yet, so whatever the total current is has to flow through R1. Okay? So that's what we find. We find that we're basically taking R2 out of commission, and R1 is there. So let's hook it up. So let's put two resistors in series. You have to go through one, then the other, like this. And then I'm going to have a piece of straight wire that I can use to create a shortcut around this one. So first let me turn it on. It looks like this. And so I'm going to do bypass surgery here. Okay? So that's exactly the analogy here. Okay? So what I'm going to do is I'm going to give a free ride from the equipotential B, which is in the middle, all the way over here. So everything is going to go through this and not through there. This is going to turn off. Okay? So notice what happens to this one. Now the entire voltage drop is here. Okay? So you can't do your bypass surgery on this section without affecting this. Okay? So if you're in some kind of cardiac surgery and you're putting in a bypass, be aware that you need to be, the blood vessels upstream and downstream are going to have an overall increase in pressure difference, okay? So is this short circuit a good thing or a bad thing? Well, let's not make it the analogy to, cardiovascular. Let's just say literally it's electricity. You work for PG&E. You want to do some work on this part safely without getting electrocuted. So you put in a bypass on purpose. So a short circuit is a good thing, right? It allows you to reroute the electricity by some shortcuts so you can do your thing. So the short circuit there, you want to do it, it's intentional, so therefore you're expecting it, it's all fine. Now, what we normally think of as short circuit is something unexpected, like you say you drop your phone in the bathtub, okay? All right, so you drop your phone in the bathtub. You didn't want to do that, okay? Well, what's happened? Moisture has gotten into your device, and water is a pretty good conductor of electricity. So if water is letting two parts of the circuit talk to each other that normally shouldn't be touching, then the electricity is going to go through the water and not through the part where it's supposed to be doing its job. So if this, for instance, this part of the thing operates the screen, then your screen goes blank, right? So there, a short circuit is a bad thing. So what do you have? Your best chance is that your phone was off at the time, right? Let it dry out. You might have a shot at it working. But the worst thing that can happen, of course, is that it's on, you drop it in the bathtub, because then the things that are still doing their job are getting stressed out more. So that's where the damage might be done that's irreparable, okay? So if you remember nothing else from my class, if you ever drop something that's electronic, if you get lucky enough that it's off when you get some water in it, let it dry out thoroughly and you might have a shot, because if you have some short circuits in there, whatever is still actually in the electrical flow gets stressed out more, okay? So that is the idea here. Now, as a final thought, let me take that bypass, and instead of making it totally free, let me make it another resistor, okay? So this is example what I started off talking about today. I'm going to change the voltage drops. Now, of course, what I just did was making this no voltage drop, so this had to take all of it. That's the easiest case, right? When I took this one out, and this had no voltage drop anymore, this had all of it. Well, you don't have to go that extreme. I am just going to make this section less resistive. Not zero resistive, but less resistive by putting something in parallel, right? So this section is going to be less resistive, and it's going to drop how much voltage drop this section takes, and this is going to take more. So let's try that. I connect this over here. So hopefully you saw that, right? So this, less voltage drop, this more. So this less dim, this more dim. I changed the ratio of resistances, so I changed the ratio of voltage drop. This less resistance, and this is going to take less of the voltage drop, and this one has more. So let me do it again in case you didn't see it. So when I make this section less resistive, it's going to drop the voltage drop here and increase it over here, okay? It's basically exactly what I just did, but not as extreme. So this didn't decrease all the way to 0. This didn't increase all the way up to that. It basically did all this stuff, just not as much, okay? So remember, when you start messing around with the resistances in series, even if you mess around with one of those resistances by making it in parallel with another resistor, that's going to change the ratio of voltage drops, okay? So you can see that, right? Okay, so let's call it a day there. We'll do kind of a big monster combo computation at the beginning of next time, and do some other cleanup for homework number 3.